Hello and welcome to the channel. Today, we're diving into a fascinating and often misunderstood topic in mathematics, complex numbers. You probably heard of them, maybe seen that mysterious letter I, and wondered, what are complex numbers actually used for? Well, in this video, we're going to explore real-world applications of complex numbers across engineering, physics, computer science, and more. Let's get started. Before we jump into applications, let's do a quick refresher. A complex number is a number of the form of plus by, where a and b are real numbers and I is an imaginary unit. Remember, I is defined as the square root of -1. While this might sound abstract, complex numbers are incredibly useful tools in many fields. They can be represented on a plane called the complex plane, where the horizontal axis is the real part and the vertical axis is the imaginary part. Now, with that foundation, let's look at where these numbers show up in real life. One of the most common applications of complex numbers is in electrical engineering, especially in the analysis of AC circuits or alternating current circuits. In AC systems, voltage and current are constantly changing direction. To model this efficiently, engineers use complex numbers. They represent voltages and currents as phasors, which are rotating vectors in a complex plane. This allows engineers to use simple algebra to solve otherwise complex differential equations. Instead of dealing with sine and cosine functions all the time, you can just use complex exponentials. That makes circuit analysis faster, cleaner, and more powerful. Complex numbers are also crucial in signal processing. When we deal with audio, images, or other digital signals, we often transform them using the Fourier transform. The Fourier transform breaks a signal into its frequency components. It represents these components using complex numbers, where magnitude tells us how strong a frequency is, and the angle or phase tells us its shift, whether it's compressing an image, filtering audio, or analyzing vibration data. Complex numbers are at the heart of it. If you've ever used an MP3, JPEG, or watched a video, you've benefited from this application. In control systems and robotics, complex numbers help model and design dynamic systems. They're especially useful in analyzing stability, using tools like the Laplace transform and bow plots. Imagine designing a self-balancing robot or a drone. You want to react smoothly to changes, not wobble or crash. By modeling the system in the frequency domain, using complex numbers, engineers can predict how the robot will respond to inputs and design better controllers. Complex numbers also play a major role in quantum mechanics. The fundamental equation of quantum physics, the Schrödinger equation, uses complex value wave functions. These wave functions describe the probability of finding particles at certain places and times. The mathematics of quantum theory simply wouldn't work without complex numbers. In fact, the entire concept of quantum interference, one particle going through two slits at once, is described using the addition of complex amplitudes. It's a beautiful and mind-bending use of math in understanding the universe. In fluid dynamics, complex numbers are used in potential flow theory to describe how fluids, like air or water, move around objects. This has applications in aerodynamics, such as designing airplane wings or predicting how smoke flows in a room. Engineers use conformal mapping, a technique that transforms complicated shapes using complex functions to solve fluid flow problems more easily. So, next time you see a plane take off, remember, complex numbers help make that possible. In computer graphics, complex numbers help create stunning images, especially fractals like the famous Mandelbrot set. Fractals are infinite patterns created by iterating simple mathematical rules using complex numbers. They're not just beautiful. They help us visualize chaos, randomness, and structure. They've also inspired compression algorithms and texture generation in games and movies. Even rendering techniques like ray tracing use concepts from complex analysis to simulate light behavior realistically. In mechanical engineering, especially in studying vibrations and mechanical waves, complex numbers simplify the math. Say you're analyzing how a building responds to an earthquake. Engineers use complex numbers to represent oscillations and dampening. This helps them predict whether the building will sway safely or collapse. whether it's bridges, engines, or skyscrapers. If it vibrates, complex numbers are probably in the calculations. So there you have it. Complex numbers aren't just abstract math. They're tools that power the technology we use every day, help us understand the universe, and even keep us safe. From electrical circuits and quantum particles to robots and fractals, complex numbers are everywhere. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell for more deep dives into the hidden math behind the world around us. See you in the next one.